Let's talk about how to do some operations with decimals. So addition is the probably easiest one to do here. So first thing I would have mentioned that I didn't really talk about in the previous section, like what is the decimal really there to do? The decimal is there to tell you where your ones place is, right? So without the decimal, if you just had the digits 1, 2, 2, 3, you would not really have an idea of like what the place value of each of these digits is. So that becomes very important when you're adding things. So, so the standard algorithm that we kind of tend to know is we would just take the two numbers and line them up vertically. And the key thing right there is we have to line up the decimal. And the reason that we line up the decimal is because we want to add each place value. We want to add all the ones together. We want to add the groups of tens together, the groups of 1/10ths, hundredths place, and then the thousandths place. Implicitly, there's a 0 for the thousandths place there. And then you can just add down, right? So we would get 28 and 719 thousandths. Now, the other way that you could think about this is to think about this as a fraction. So 12 and 23 hundredths plus 16 and 489 thousandths. You could add this the same way that you would add any fractions. So when you're adding fractions, what do? You have to find a common denominator, which is very easy to do when you're working with decimals because everything's just powers of 10. So you could just multiply by 10 over 10, which just amounts to inserting some extra zeros over here. So now your common denominator is 1,000, and now you can just add accordingly. So we get 28 when we add the 12 and the 16, and then we're going to get whatever 489 plus 230 is. You add that, and you're just going to get 719, similar to over here. So we'll get 719 thousandths. And so in total, you would get 28 and 719 thousandths. All right, which is the same as this number over here, just written a little bit differently. And so you can kind of see that the steps are like really mirrored in both of the methods. Like this implicit 0 over there, like that's kind of thrown in because that's what that's doing, is that's just mirroring finding the common denominator. And then all of the other steps that we do are kind of the same. Like when we had to like line these up, if these were more complicated numbers, we might have to line those up as well. And so like the steps are really like the same in either way. What about multiplying? So if I want to take something like 1 and 23 hundredths times 2 and 6/10, how do we multiply those together? Well, the standard decimal multiplication algorithm that you could do first says just ignore the decimals. So just multiply these two numbers as whole numbers and then worry about the decimal later. And what do you do when you finish multiplying and then have to throw in the decimal? Well, what you do when you're doing this, when you're moving the decimal over, you're multiplying this number by 100 to move the decimal over twice, and then multiplying this number by 10 to move the decimal over once. Right? So we're basically multiplying by 10 3 times total, because this is like 10 squared and then 10 to the first. So there's 3 extra factors of 10 in there. And so at the end, once we get our final answer, we're going to have to divide that by 10 3 times. So that amounts to moving the decimal over 3 spots at the end. So here I have this worked out. So ignore the decimal for now. So 123 times 26, 123 times 6, so you get 738. 123 times 2, you get 246. Add that up, you get 3,198. If we are just doing this with whole numbers, this would really be 3,198, but we have 3 extra factors of 10 that we multiplied by here, so we have to move the decimal back 3 places by dividing by 10 cubed at the end. So we get 3 and 198 thousandths, or 3.198. All right. What about when we have like excessive amounts of powers of 10 in here? So this is when scientific notation comes into play. So scientific notation is when you represent a number as just some number that's between 1 and 10 times 10 to some power. So this is 3.1 times 10 to some power. So how many zeros are there? 1, 2, 3, 4, 5, 6. And then we're going to move the decimal over one more time. So there's like really 7. We multiply by 10 7 times here. Okay. So like that's scientific notation for the first number. And the second one would be 4.8 times 10 to the 5th, because 4.8 times 10 to the 5th, you would go 1, 2, 3, 4, 5, and you get the 4 zeros that way. Okay, so that's scientific notation. And then from there, you can multiply these numbers. So 3.1 times 4.8. Did I do it already? No, I didn't do it. So I'll just do it real quick. So 8, 24, and then throw in the 0, 4, 12, add it up, 8, 2, 4, 1. Okay, and then we throw in the decimal right here, so because we multiplied by 10 twice, so move back 2 times. So that's what 3.1 times 4.8 is. So 14 and 88 hundredths, and then times 10 to the 12th, because that's 10 to the 7th times 10 to the 5th. If you want to represent this as a number in scientific notation, though, you would have to move this decimal back 1 and then add another 10 over here. All right, so that's using scientific notation. Let's move on to division. So if I want to do something like 22 56 hundredths divided by 1 and 6 tenths, how do we do that? All right, so using an algorithm, what you can do. So the first thing that you're going to want to do is have as few decimals in the problem as possible. So usually the number that you're dividing by, you want that to be a whole number. So when you're taking two numbers and dividing them, so let's say that I'm taking like, I don't know, what's a good example? 16 divided by 4. You could divide both of these numbers by the same thing, and that's not going to change your answer. 16 divided by 4, we know is equal to 4, but if we took both these numbers and divided it by 2, so we get 8 divided by 2, it's still going to be 4. If we were to multiply them by 2, you get like 32 divided by 8, still going to be 4. So if you multiply or divide these numbers by the same thing, that's not going to change your answer. Same thing for if you were to like divide by 10 or multiply by 10. So if you divided them both by 10, how many times does 0.4 go into 1.6? It will go in there 4 times. So effectively, you can move the decimal the same number of places for both of these numbers, and it's not going to change your final answer. So make this a whole number by moving the decimal over once. So we're multiplying it by 10, and then do the same for this other number. Okay. There's still going to be like a decimal part here. There's still going to be like a fractional part at the end, but that's fine. We still just kind of ignore it, and then just do the long division as normal. So 16, how many times does 16 go into 22? Goes in there once. So take that away, you're left with 6. Bring down the 5. 65, 16 goes into 65 4 times, you get 64. Take that away, you're left with 1. Carry the 6. How many times does 16 go into 16? Just once. Okay. And then we ignore the decimals up to that point. And when we do this, we have to bring this decimal up here, essentially, just lining up the place values. Okay. And again, very similar to what was happening with the addition. The whole point of like, why does the decimal go here? It's really just according to place values. Okay. Right. All right. So last time in the last section, we talked about how to represent something like 5/8 as a decimal, but we did not talk about how to do this using a division algorithm. So you could do this with a standard division algorithm by doing just 5 divided by 8, and then just write this as like 5.000 with as many zeros as you want, and then just do division. Okay, so 8 does not go into 5 any times. We'll put this decimal up here. How many times does 8 go into 50? It goes in there 6 times. So 6 times 8 is 48. So bring that down, left with 2. Bring down the 0. 8 goes into 20 2 times. Get 16. 4. Bring down the 0. And then 8 goes into 40 5 times. And then we get a remainder of 0. And since we got a remainder of 0, then like everything else past here would just be zeros, and we can really just stop, right? So 5/8 is equal to 625 thousandths as a decimal. Okay. It gets a little bit more complicated when you have something like 2/11ths, which is not going to give you something that terminates. So over here, this we would call a terminating decimal. So this is terminating. So what do we get for, what do non-terminating decimals look like? So 2/11ths, let's do it for that. So 2 divided by 11. All right, how many times does 11 go into 2? 0 times. How many times does it go into 20? Once. Ignore the decimal. We get a 9. Bring down a 0. How many times does 11 go into 90? 8 times. You get 88. And then you get a 2. And then you can continue on. Just bring down that 0. How many times does 11 go into 20? Goes in there once. How many times does 11 go into 90? 8 times. And you get a 2 again. And then you can just repeat this, right? So you're just, you can see that there's like a pattern here. Like you're just going to alternate remainders of 9s and 2s every time, right? And so this pattern up here just repeats, like it's repeating between 1s and 8s all the time, okay? And so we would call this a repeating decimal. And so we would write this as 0.18 with the bar over it. And the bar represents the fact that that part of the decimal is repeating. So this is like a different number from something like this. And it's also a different number from something like this. So this right here is like 0.0181818. This one right here is 0.018018018 because the bar means, oh, the whole thing 018 is repeating. And here, this 0 part isn't repeating at all, but the 18 part is repeating. Okay, so that's a repeating decimal. There are also non-repeating decimals. For example, pies. If you want to represent pi as a decimal, that would give you a non-repeating decimal. But yeah. If you want to do something like 2/7, that is also going to end up being a repeating decimal. So this one is a little bit longer, so I just wrote it out ahead of time. So divide 2 by 7, and you're going to get 0.285714. And then how do you know when it's going to start repeating? Well, you know it's going to start repeating once you start seeing the same remainders again. So we divided by a 2 at the beginning, and then you just look for the next time that you have to divide by 2, and that happens all the way down here. And so if you were to repeat this process, the next remainder that you would get would be a 6, and the next remainder you would get would be a 4, and then a 5, and then a 1, and a 3, and then a 2 again. And you would just get these same quotients up here. And so 2/7 is equal to 2, 8, 5, 7, 1, 4, all repeating. So it's a little bit longer, but it still works.